Hi, uh, in this presentation I'm going to introduce Flint. Flint is a platform for running Spark streaming application on a cluster. Before I start this presentation, let me introduce our team. I and Ohchan, Kwon and Dongwoo team, we are a team and we develop Flint together. If you have any question, then please raise your hand anytime. And after a brief introduction of this Flint, we will show you a demo. So please do not leave early. Okay, I guess you guys all know what Spark streaming is. The problem that we want to focus on is how this Spark streaming application reacts to a sudden increase in rate or decrease in rate. If a Spark streaming application is allocated to fixed amount of resources all the time, then if event rate becomes too great, then it can't process those streams in time. So the application has to store pending events, and this can exhaust application's resources. Okay, I think you all heard of dynamic resource allocation. It reduces executors if the executors becomes idle too much, or it increases executors if the task pending time is too much. But I think we think that batch processing is better metric to assess the workload for Spark streaming application, and we think the random nature of Spark scheduler makes scaling hard to occur in practice. And batch pressure is about reducing the event rate by signaling back to the event source. But we'd like to have a solution to which makes this application to process events in real time. Back pressure is not a solution for that, so we made our own solution, which is called Flint. This is the architecture of Flint. A Spark application runs on its own yarn cluster, and this yarn cluster is deployed on a Mesos cluster. We chose this architecture because we wanted to run a variety of applications on our cluster. Those applications may not be yarn application, no Spark applications. But still, we wanted a Spark on yarn deployment model because Spark on Mesos does not allow multiple executors to run on the same slave host. Also, in Spark on Mesos, executors may have different number of CPU cores, and this makes it very complicated for resource management. To launch a Spark application, Flint first requests Marathon to create yarn cluster. Then Marathon deploys yarn components on Mesos. These yarn components are Docker containers. After that, Flint submits Spark application on the yarn cluster. This slide shows how Flint triggers scale in or scale out. In Spark streaming, batch processing time should be shorter than batch interval. So Flint tries to keep the batch processing time within two thresholds, and of course these two thresholds are configurable. Flint keeps monitoring batch processing time and compares it to the batch interval. And if the processing is completed too early, Flint scales in the application. If the processing takes too long, then Flint scales out the application. This is the scale-out process. First, we grow the size of the yarn cluster by requesting Marathon to deploy more node manager Docker containers. And after the yarn cluster gets larger, Then we signal the application to request more executors from Yan. And this is how scaling is done. First, we carefully choose executors here. These executors have least number of RDDs, so they can be killed without degrading application performance. We do not kill them right away because there may be running tasks on them. So we first exclude them from scheduling and actually kill them after the tasks are completed. After that, we reduce the size of Yan cluster. This is done by decommissioning node managers and killing the corresponding Docker containers. These are the issues we faced while developing Flint. We needed to add several REST APIs to Spark, which are returning batch processing time and adding or removing executors. And we also added a new method to RDD, which is repartition. This sets the number of partitions based on the current number of executors. If we don't do this, we may not benefit from more executors. We optimized the scaling as well. We should prevent Spark from trying to reconnect to dead executors for shuffle data or for running tasks. So before actually killing executors, we advertise the victims to make shuffle requests to them fairly fast. We also reduced data locality wait time, so scheduler does not wait too long for data local executors. Also, in scale out, Docker images download or Yan localization make too much disk access. And this disk access is not good for the performance of the application. This can be solved by preloading those data, or we can use separate disks or SSD. Lastly, we noticed that block replication to new executors sometimes take too much time. So we do not replicate blocks to new executors for a certain amount of time. We are planning to open source this Flint project, and for those Spark modifications, we will post patches as Jira items. Now let's see demo. The application is a log analyzer. It takes log messages from a commercialized service. This is the log message rate for a day. We will deploy this application using Flint, and we'll see how Flint scales out the application when log message rate increases. This is the Flint dashboard. I'm going to request Flint to launch the log analyzer. And this is Marathon. It is now deploying Yan cluster. If Docker images are downloaded, Yan cluster is created under a minute. And this is the web UI of the just created Yan resource manager. As you can see, we have the specified number of node managers. And now let's see the Spark web UI. If I replay the log messages, the batch processing time starts to increase. And as the log message rate becomes higher, processing time becomes longer. And Flint scales out the application by adding more executors. And now it's scale in. We are going to deploy the log analyzer with 15 executors, and we will reproduce the log messages, and the rate of this log message is not high, so we don't need these 15 executors. So as you can see, Flint continues to scale in the application until the batch processing time becomes the in-between of the scale in and scale out threshold.